In this video, we're going to take a look at how to get this OLED display working. OLED stands for Organic LED. It's quite a nice little display. I'll have a look at it compared to the last display we looked at, which was the 5110 display. You can see it's quite a bit smaller, but it actually has a higher dots per inch count. So we've actually got a higher resolution on this display. It's also quite different in the way that this display here shows a black text on this kind of grey background. If we were to look at it without light on it, we wouldn't see the display. That's why we've actually got a built-in backlight. This one here, the actual pixels themselves produce light. So there isn't a backlight, the screen is dark, but when the pixels turn on, they actually are illuminated. So it's quite a nice little display. Especially for dark scenarios where we haven't got light. The disadvantage to this one is that we can't actually turn that light off. We don't have the option of turning the backlight off. So in fact this one consumes a little bit more power depending on how many LED pixels you have switched on. This one here will consume more power with the backlight on at full, but will actually consume less power with the backlight off. That being said, it's very, very small, so we can make a very small device here. You could build a little ring mounted computer or something if you had a small enough microcontroller. Some other advantages to this one here is it only has 4 pins on it. It has a positive, a ground, an SDA and an SCL. So this one is using half as many pins as this device here. The next thing to note is this is what we call an I2c device or an I2 device. That means it has the 2 pins and it has the SDA and the SCL. There is another version called an SPI device. This example will not get the SPI device working. You will need a different example to get that one working. The way you can tell them apart is the SPI device has more pins, and it will have probably at least 6 pins across the back here, maybe even more. So if you've got 4 pins on the back, it's definitely an I2c, and that will need less pins. Okay, so let's go ahead and connect this up to the Arduino, and to do that we're going to need 4 wires and of course our microcontroller. So we've got our 4 connectors here, and I'm just going to connect these up nice and quick. So we've got ground, VCC, SCL and SDA. Then we're going to connect these up to our microcontroller. So we're going to take the ground to ground. We're going to take the VCC to 5 volts, and then the SCL pin, that can go to 2 places actually. There is an SCL pin on this side of the microcontroller, so up by the USB port there's one, but there's also a second breakout where we can connect to it, and I believe that one is a 5. So we could connect it over here, SCL to SCL, or we could connect it up to A5 over this side, which just I think makes it a little easier in this case. And then finally our SDA pin will connect to either the SDA on this side, or we can go to A4 on this side. So we'll connect that one up to A4. And that's nice and simple. Now we can actually connect to multiple devices down these 2 wires, and to do that these devices actually have a built-in address. As we look at the back of the board, there's actually a little kind of resistor that's soldered into different positions to give it a different address. And in a minute when we look at the code, I'll mention the addresses again, but we kind of have to guess which address this is. The only way we could find out for sure is you can get some example code, which is called an address scanner, and essentially you install the code on the microcontroller. It scans through all the various addresses, combinations that this could be, and then on your serial monitor it will come back and tell you where it's found a device. That way we could have multiple screens on these same wires kind of daisy chained along, and as long as we change the addresses before we sent the data to them, we could use multiple, or we could have a temperature sensor or a gyroscope sensor on the same wires, and we could basically say from this address receive the data, to this address send the data, and they would sort themselves out that way. Okay, well the connections are nice and easy, there's only 4 wires, so let's go over to our program and see if we can get this thing going. Okay, and just as before, I've put a little test code up onto this GitHub folder here. So if we open that, which is the OLED display, we can see this example code, and we can either select it all and copy it, or we can just use this button to copy the data. And then what we'll do is we'll open up a blank sketch, paste in the code, and then we'll actually save that. You want to save that as OLED test or something like that. And then we'll just quickly go through this test code before uploading it. So this is a basic test code for the I2c type. It doesn't support the SPI type. We know it's the I2c type because it has the two data pins, SDA and SCL. They can be connected to your microcontroller SDA. If you're working with a nano device, it might not have an SDA pin, so in that case you can use A4, and the SCL can go to SCL or A5. We're going to need these two libraries. If you followed my previous tutorial, you should already have this library, so no need to reinstall it. And we're also going to need the Adafruit SSD 1306. So if you haven't got that one installed already, go to your library manager and download that. The next thing to note is that these displays come in two different main sizes. There are other sizes, but the common ones are 128 pixels wide by either 32 or 64 pixels high. Now I know mine is a 64, but if you were to put 32 in there and you found that it didn't look right on the screen, as in there was like rows of pixels that weren't filled up, you'd need to change that to 64. And of course, if you bought the 32 pixel device, you'd need to change that to 32. Next, we have the address of the device. I found that the address on mine is 0x3c. A common alternative address for these displays is 0x3d. So if you program this in and you find no response from your display, first of all check your connections are correct, then maybe try changing the pixel height, and if that doesn't work, do actually change over your address. Now if all else fails, you might have a device with a completely different address. If that's the case, you're going to have to do a search online for a tutorial telling you how to scan the I2c port for the device address, and you'll basically copy and paste a new bit of code, install it into the microcontroller, and then you'll open your serial monitor up, and the serial monitor will provide you with the address that your device is assigned. In this example, we're going to use two ints, a timer and a counter. I could have just called it timer and counter, but I called it a timer, a counter, and we've set them both to 0. This next bit of code here is actually going to send the number of pixels wide and the number of pixels high that we've just set up here to the library to get the device configured properly. And then in our void setup, we're just going to go through, set up the display. So we actually use this begin OLED address line that kind of passes some data to the library and turns the device on. Now, when it comes back from that code, it actually comes back with some graphics. It comes back with the Adafruit library graphics. Thank you very much to Adafruit for making this library here. Very powerful library. And if you've got a chance, after you've installed the library, do look at the examples. We go to File, Examples, and we can go down to the SSD 1306, and we can see there's versions down here that support your I2c and your SPI at various different sizes. Now if I open one of these up, you'll actually see this is a really huge bit of test code. Let me scan down here. We've got lines after lines after lines of code, and that does actually manage to present some really nice graphics, some different kind of graphical effects onto the display. But if we just want to display some text and numbers, it can take a while to work your way back through this code, figure out exactly what you want. What you do want is probably the stuff towards the end of this program. So to minimize stuff, I've put together this code that is kind of the bare minimum. So as I was saying, when we've sent this line of code to the library, it's going to come back with the buffer that holds the data to go to the display full of graphical data with the Adafruit logo. Now to get rid of that, I've actually just sent the clear display command there. That clears the buffer. Next thing we're going to do is set the text color. This will actually set our text to white with the black background. I believe it should support screens of different colors as well. but not multiple colours, only the kind of black background, blue text, or black background and yellow text. This one is a black background with white text. Next thing, we've got our font size set to 1, and just like we did with the 5110 display, we're going to set our cursor position to 00, and then we're going to send the text message OLED test code to the display buffer, and then we use display to actually pipe that buffer data out to the display. Then we have a delay of 2 seconds just so we can see that display, and then we're going to clear that buffer, because otherwise when we get down to the next row it will still have some of this data in the buffer. So it's good practice to clear our buffer. Remember, this is in our setup area, so this will happen once. We'll print OLED test code for 2 seconds, and then when we come down to our loop, we're going to display some different things. So we're going to start off by clearing that display buffer. Now, I know we have just done it above, but in a minute we're going to loop through this code repeatedly, and when we get to the top we want to kind of clear that buffer again. So we'll start off with a clear buffer. We'll also set the text to white, as it's good practice, that's what we want at this point. Then we'll update a timer with the current milliseconds value from the internal clock. Then we will increment the A counter by 1 every time we loop around. We're then going to set our text size to 1, our cursor position to 00, and then we're going to print the text timer equals, and then we'll actually print the A timer variable value. Now note that we haven't sent this to the display yet, because we can actually do lots of things one after another, and then at the end we'll send it to the display. So the next thing we're going to do is set the text size to 2, change the cursor position 0 to 10. Remember, it's going to be the first number is going across the display, the second number is going down the display. And then we're going to print the text word C equals, and then we're going to follow that with a print display of the A counter variable. Remember the drop of the speech marks when it's a variable, putting speech marks in when it is actually text. Now actually, I found that this library requires a double bracket to be used when we're sending text. So notice there the double brackets, but actually when we send the variable value, we don't use the double brackets. Now we're going to step down and we're going to drop back from text size 2 to text size 1. We're going to move our cursor across 0 down 30 pixels. Then we're going to use the following command here to actually invert the colour. So now instead of it being a black background with white text, we're actually going to blot the background out white and put black text on it, which gives a kind of nice effect. And in that block of white background we're going to print the text word inverted. Now I haven't actually used the brackets on this one, so maybe I don't actually need these brackets. I'm going to take them out. I think it works either way, with the double brackets or without the double brackets. So that's interesting. We'll carry on. So once we've printed that inverted, we're then going to change the text size to 3. It may support larger text sizes, but I've only tested up to 3 in this example. We're going to set our text colour to white again on the black background. We're going to move our cursor 20 across, 40 down, and then we're going to display print the text ... 3. And then right at the end of all that we do our display, and then we're going to wait 1/4 of a second before we go back to the top. And when we get back to the top, we want to clear that buffer out, ready for all of that to be reprinted in it. So clear the buffer and we're ready to go again. And of course the only thing that will change is the A timer value and the A counter value. Okay, let's upload that and see what happens. And there it is. Hopefully you saw it said OLED test code at the top briefly for 2 seconds. Then we come down and we've got our timer that's updating as we loop around in our program. Notice the text size 1 there is quite small. It's just legible, not bad for the size of the screen. Then notice that when we've moved to text size 2 for the C count, or the count there, it's quite a bit bigger. So it uses up a fair bit more screen. Then we move down to our word inverted that's been printed on the white background with the black text. It does look just about legible by the eye. It might not look as good on the camera. And then we go down to our text size 3, where we printed ... 3. And remember, we need to clear that buffer before presenting it once it's filled up at the end. So not a bad little display, only uses 4 wires and is fairly quick to get going. And anywhere where your project needs a lot of microcontroller pins, this display is a perfect solution. Well, thanks for watching, and of course make sure to like and subscribe, and I'll be covering more devices in the future.